Thank you for coming to my discussion today of my master's thesis research. I'm Abigail Heath. I'm a Master's of Hydrogeology student at Illinois State University, and my study looked at natural nitrate removal in shallow subsurface stream flows. So, um, nitrate is a naturally occurring nutrient. It's vital to a lot of different organisms in the environment. So it does occur in the environment, and it is very important to occur in the environment. But because it's so important, it's been applied in increasingly excessive quantities to the environment, specifically in agricultural settings as agricultural fertilizer. And it's via runoff from these agricultural fields, it's led to a lot of buildup in stream systems. And as you can see in this lower photo here, this is an algal bloom in a stream system here, and algal blooms can lead to really a breakdown of aquatic ecosystems, as well as dangerous health conditions for humans who ingest this water. So understanding how streams can help to mend their own levels of excess nitrate and to process and remove that nitrate could be really helpful to future remediation projects in determining how we can remediate streams and engineer streams to best improve their own water quality. And one of the potential ways that streams can help to reduce their own nitrate levels is via this shallow subsurface flow zone just below the stream bed called the hyporheic zone. So the hyporheic zone is a zone where you have infiltrating stream water and upwelling surface water, upwelling groundwater. And this zone has kind of a unique chemistry where it's a combination of the distinctive stream and groundwater chemistries that you see in a stream environment. And so in this zone, there is this potential for nitrate to be processed and removed from stream water. So my project looked at what is the actual quantity of infiltrating stream water versus upwelling groundwater that we see in this shallow subsurface flow zone below stream beds. And then what is the trend of nitrate removal that we see along the depth of this mixing zone, as well as into the banks of the stream setting, so that we can kind of determine how much water mixing we're seeing and how that relates to the potential for nitrate removal in streams, so that we can hopefully apply that to future engineering projects, stream remediation projects, on a quantifiable level. My study area was the T3 stream. It's about 10 miles north of the Illinois State University campus. And as you can see from this photo, it's surrounded by agricultural fields. So this stream was a really great place to study what stream environments that are experiencing that excess nitrate level that we're seeing in runoff entering these agricultural streams. And so as you can see from this map here, this stream, it kind of is, so it's surrounded by these agricultural fields. There's a lot of ground wells here in this study area, but I specifically inserted 3 multi-sampler wells into the stream bed itself along the length of the stream here. And then I also had a well here right in the bank where I was collecting groundwater samples. And so I was collecting samples from the stream, from that hyporheic zone, as well as from the bank groundwater. And then I was comparing the chemistries from those different samples. And so as you can see, I was able to sample along the entire depth of this mixing zone in the stream bed, as well as sample from the riparian zone at about that same depth as the hyporheic zone. So I was able to really observe the exchange and the extent of that exchange within this specific stream. And I sampled I sampled in spring, summer, and fall of the past year. Due to COVID, that it wasn't consistently spring through fall. I did collect some of my spring samples this year in this past March, but basically I got a good understanding of the spring, summer, and fall levels of mixing in this mixing zone, as well as levels of nitrate that we're seeing in this zone. And so I analyzed these collected samples on an ion chromatograph, looking for major anions, but more specifically nitrate and chloride. Because I collected the nitrate because, of course, I was looking at those nitrate levels that we're seeing, but I was also really looking for chloride because chloride is a conservative ion that you can use to determine specifically that movement of water through the system. So unlike nitrate, which changes as it moves through the system, chloride was more reliable to help create this model of what the amount of surface water infiltration that we saw along depth through this mixing zone, as well as the amount of nitrate we expected to see based on that infiltration. So first I calculated the amount of water that we saw infiltrating throughout this flow zone, and then I used that amount of infiltrating water to determine the amount of nitrate we expected to see based on the mixing. So firstly, what we saw in the actual measured samples was we saw that up here in the stream itself, that's what is denoted as like the 0 centimeters depth. That's the actual stream. We saw the highest levels of nitrate across the board. We also saw the highest levels of chloride across the board. And then down here in the groundwater, we saw the lowest levels of both nitrate and chloride. And then here, from that 10 centimeters below the stream bed to 50 centimeters below the stream bed, you have the extent of that hyporic mixing flow zone below the stream bed. And you can consistently see that these measured nitrate levels that we saw, they decreased in concentration along depth. So highest at the top of that hyporic zone and then lowest at the bottom with that decrease. You saw that both with nitrate and chloride. And so in our model, we saw that you can see here the triangles are the modeled and the circles are the actual measured. We saw the same pattern, highest nitrate at surface, lowest at depth, and then we saw that general decrease along the depth of a hyporic zone. And this completely aligns also with that amount of surface water infiltration. So while just like with this graph, we saw a difference in magnitude between the summer samples and the fall trend of the samples, we saw the highest level of surface water infiltration at surface, or near surface, and then the lowest at depth. However, at depth, at surface in the summer, we saw over 75% infiltration at that 10 centimeter depth below the stream bed. And at 50 centimeters at the bottom of this mixing zone, we saw over 50% infiltration. And then in the winter, we still saw over 30% infiltration at depth. In this mixing zone. So this zone is being thoroughly mixed. And then in terms of that nitrate trend that we're seeing, nitrate is being removed along depth. There's a slight increase here at 20 centimeters, but really along depth, you can see there's a discrepancy between that modeled level of nitrate that we expected to see and the actual measured level. And that indicates that there is removal of nitrate along the entire depth. And you see, I mean, it's a lot closer over here in the fall, winter months, but really you're seeing that there is a removal of nitrate across the board. So this study shows that there is thorough mixing of surface water and groundwater in this shallow subsurface flow zone below stream beds. And in this flow zone along depth, we're seeing nitrate being removed. In the stream banks, we did not really see a connection between the stream water and the groundwater. Pretty much that groundwater went right up to that stream groundwater interface. But along just below the stream, and along the length below the stream, we were seeing this processing and removal of nitrate. And so taking these quantities, we can perform further research to determine exactly what processes are occurring in the future, and maybe take that and really determine how do we engineer streams in future remediation projects, and how do we foster healthy streams in the future to support this optimum level of nitrate removal that we want to see in streams that are gaining that excess nitrate from anthropogenic inputs. So I'd like to acknowledge my thesis committee, as well as all of my helpful field assistants in helping me throughout this project, as well as the generous funding support of the Illinois Water Resources Center and Illinois Lakes Management Association, and the City of Bloomington for allowing me to access this stream site. Here are my references, and thank you so much for attending my talk, and I'm happy to answer questions.
Yes, we have time for several questions.
I don't have any yet.
I'll ask one while we're waiting for questions to come in. I know you haven't analyzed this yet, but what do you suspect are some ways that could engineer a stream to enhance nitrogen removal?
Well, I think that a lot of what is contributing, I guess I can't definitively speak to the processes that are removing the nitrate in the stream. We're thinking it's probably not plant uptake, because we didn't see a lot of plants in this stream, at least in the case of this stream. So I'm thinking in terms of like how much water mixing we're seeing in that subsurface zone. That's really key to the amount of nitrate removal that we're seeing. And so engineering streams that have the right geomorphology, that allow water to flow for more extended periods in this subsurface zone and to mix more thoroughly in that zone, that is going to be important, I think, for future projects.
Do we have time for another question?
Yes.
Okay. Interesting study. Should nitrate-laden discharge be held back during low flows?
I'm not sure about that, because it's still potentially going to be entering the system in another way, through infiltration just into the ground. So it has to be processed somewhere. And also, we saw pretty low flows throughout this study. It was kind of a dry year here in Illinois. So, and we still probably didn't see necessarily a change from the amount of flow in terms of the levels of nitrate that we were seeing, as far as I could tell. So I think it's more maybe other solutions potentially.